Hey Kim, how was class today?
It was not too bad. My students actually understood most of amines today.
Oh, that's great, that's great.
Yeah.
Okay.
Oh, you guys are here.
Hey.
Hello. Hey, how was lesson today?
Oh, I think it was pretty good actually. Yeah.
Good.
Okay.
Make sure to watch your post-lesson video, yeah? No more pre, okay?
No problem.
City Hall. Please mind the platform gap.
I'll go first. Yeah, be careful, be careful.
Sorry.
We hear you.
Alright, so guys, so no more pre-lesson video, and welcome to...
Post-lesson videos. Right, so what's going to happen in the post-lesson videos, we're going to capture the most important concepts that we have done during the lesson itself. So this will help you in the revision before your exams. And what we're going to focus on again? The most important concepts.
Okay guys, as usual, before we start, take out your
Encyclopedia.
Okay guys, so we're going to revise what we learned in class, and what we learned in class today was amines, right? So very quickly, just remind yourself an amine, right, is what we call an NH2 group directly bonded to a carbon. Now the carbon can be saturated, like what you see here, or it can be part of a benzene ring, it doesn't matter, okay? Just take note. Now, we're going to learn how to prepare amines, and altogether we have
4 reactions.
Perfect, right? But we're only going to be focusing on one, okay? And it will be this one. To prepare a phenylamine, we're going to start with a nitrobenzene, okay? Now this reaction is important. Now, so how do you understand this reaction instead of memorizing the R and C's? So this is how you do it. You can start with a very simple half equation, taking a nitro group and reducing it to a amine group, amino group. Write the half equation here using KOHE. You can realize that you need a source of electrons and you need source of H plus ions, right? Now, Mr. William, you're going to guide me through a little bit.
Yep.
Tell me, where do these electrons come from?
Well, the electrons actually come from tin. So you notice in your notes we have tin. And what tin does is tin goes through the oxidation process.
Right.
In the midst of doing so, electrons are being produced. And electrons therefore becomes the reducing agent for us to do the reduction.
Ah, perfect. Okay. So that's where electrons come from. Now, where H plus comes from is going to be from your acid. That's why we need tin. We also need conHCl. The HCl, like I said, provides the H plus that you need. Perfect, right? So using electrons, using H plus, we can successfully reduce nitro into amine. But the thing that confuses me and most students is this. Mr. William, what on earth is this for?
Yeah, it looks very strange because you were first adding an acid in and later you're adding a base in. So doesn't the base neutralize the acid away? What's the reason for us doing so? It's really a lot to do with the chemistry of the products, right? If you notice the products that's being formed, phenylamine is actually basic in nature. Okay, we take a look at the next page of your notes, right? So if you recall what was being done in class, right, we did mention to you what is our desired product. Our desired product is going to be the phenylamine, but because the environment is acidic in nature, what will happen is the base, phenylamine, is going to react with the H plus, which is acidic, and we're going to do an acid-base reaction. So by the end of the acid-base reaction, what will happen to the phenylamine is you're going to form the salts, which can be also described as the conjugate acid, right? So what we wanted was, we wanted this, but it's inevitable. There's going to be the acid-base reaction. We will end up with the salts instead. So to overcome this problem, the next thing we got to do is we have to add in NaOH, because what the NaOH does is, this is a base, and the base will then react with the conjugate acid. They will do another acid-base reaction, and then you get back your desired product. And you notice the way that we get your desired product is by this process which is called distillation. Right, so Mr. Tim, can you remind us what's the principle for distillation again?
Well, in distillation, when we distill things, the lowest boiling point molecule escapes first, right?
Yep, right. So it has a lot to do with the chemical bonding of the substances that we have, right? So looking at this, what kind of bonding do you think they're going to have?
Well, I see a positively charged cation, right? So most probably ionic bonding.
Yep, you're right. So we expect this guy to be doing ionic bonding. What about the phenylamine?
Well, I see a H directly bonded to an N in the phenylamine, so hydrogen bonding.
Yep, you're right. Okay, so what happens now is you compare H bonding against ionic bonding, and we know that H bonding is generally weaker So the one is weaker is expected to have the lower boiling point, and therefore we expect them to be distilled out of the mixture.
Perfect.
Right, so just notice this reduction is done in a very strange manner because we are using thin, and take note, thin is not a catalyst, right? A lot of people will think it's a catalyst, it's not, right? What it does is a reducing agent to reduce this, and we can't use our typical reducing agent, lithium aluminum hydride. Hey guys, the next concept we're going to look at is basicity of amines. Right, so we recall the basics. Amines are very similar to ammonia. They're basic in nature, and the reason for them doing so is because they have lone pairs on the nitrogen. Right, so you can look at the notes, they have lone pairs, and this lone pair have the ability to accept H+. So you saw the mechanism, it will grab H+ from water, so the end result is you end up with conjugate acid, and you also notice that OH- is produced at the end of the reaction, which will account for the basic property of amines. Now, if you recall, there are two types of bases in our syllabus, right, Mr. Tim?
Yeah.
What are the two types of bases again?
Well, we have Lewis bases and we have Bronsted bases.
Right, so we have Lewis bases, we have Bronsted bases. Can you bring us through the definition again?
Yeah, for sure. So a Lewis base, remember, is a lone pair donor, right? You give your lone pair away, and a Bronsted base is when you accept a proton.
Alright, so this is a proton acceptor.
Yeah.
Okay, can you walk us through the difference
Yeah,
in
of course.
gaseous phase as well as in aqueous medium?
Okay, so let's think about this first, right? So I will talk about Bronsted bases first. Now, to accept a proton, there needs to be water present, right? Because water is a source of proton, we learned that. So you can see here, amines only behave as Bronsted bases when there is water present, so aqueous medium. And you can do this with me, again, once more. Tell yourself, you see this lone pair here? We're going to grab this H+ from the water, kick out the OH-, same idea. So if I'm grabbing a H+, I'm basically behaving as a Bronsted base, right? So we usually say that amines are Bronsted bases in aqueous medium. Now, but if there's no water present, then I can't grab a H+. I have to donate my lone pair instead without grabbing a H+. So therefore, if there's no H+ to grab, I'm going to behave as a Lewis base, where I just donate my lone pair. Now, here comes the main idea of this. We learned that in the gaseous phase, the more available your lone pair is, right? The more available it is, the stronger of a base it becomes, the stronger of a Lewis base. Now, remind me again, Mr. Rhythm, what I have here for you, it's a primary amine on the left, right? And a tertiary amine on the right. Remind me, R groups, are they electron withdrawing or donating?
R groups are electron donating.
Right, so if I donate electrons to this nitrogen, right, say same thing, all these R groups donate electrons to this nitrogen, can you tell me which lone pair will be more available?
The one that has more friends that are electron donating in nature. So it has to be the tertiary amine.
Yes. So this lone pair, because it's having more friends, right, or receives money or electrons from him, this lone pair becomes fatter, right, and hence is more available. So we say that tertiary amines, they're actually stronger Lewis bases than primary amines. Okay, that's it. So I actually don't have many friends. So I'm not very available.
Unfortunately, I'm one of his friends.
Okay, and that's it. And this is basically what basicity is about. All right, for amines.
Now, one of the most common questions you'll find in exams is to explain relative basicity, right? So there are different ways for us to explain, but the most commonly accepted way is to really focus on the lone pair availability. Right? So if you look at your notes, we have the explanations over there. If I were to compare two types of amines, now number one, which is what we call alkyl amine, right? And number two, which is what we call phenylamine, you'll notice that they have different basicity, right? So what is the key thing to focus on again, Mr. Tim?
Availability of the lone pair.
Exactly, right? So we're going to look at the lone pair, and we basically are asking this question, how available is the lone pair? Right? The more available it is, the more basic it becomes. And it always depends on the kind of friends that they have, alright? So in this case, what do we have? We have someone that is electron donating, right? So that is going to increase the availability of the lone pair. So we expect this guy to be pretty basic. But what happens in the case of phenylamine, Mr. Tim?
Well, I see a lone pair, the lone pair on the end is directly bonded to a pi system, which means the lone pair, yes, in the p orbital, the p orbitals there, they'll be parallel to each other, number one, and they're adjacent. Now, which means you're going to see delocalization, and that lone pair gets sucked into the benzene ring and is not available.
Exactly, alright. So what happens now, you can see the lone pair crosses itself into the ring, it is less available, and therefore it is less basic in nature. Alright, so that's how we explain basicity.
Alright students, so no more basicity, boring stuff. Let's learn how amines actually react. Now, before again we look at whether a molecule, how it reacts, you need to think about whether it's a nucleophile or an electrophile, okay? Now, in amine, the instant I see the lone pair on the end, right, it makes amines, like we learned in class, nucleophilic, okay? And of course, if they are nucleophilic, then they would attack
Electrophiles.
Yeah, that's it. Okay. Now, in this part, we're going to compare nucleophilicity. So what I have for you here, again, very similar to the idea of basicity. I have a primary amine here, and I also have a phenylamine here. Now, once again, the more available the lone pair is, the stronger of a nucleophile it becomes. Okay. And as usual, Mr. William, our groups are electron
Donating.
Yep, push electrons in. This lone pair becomes a more available lone pair, and therefore more basic, right? Now, for the one at the bottom, again, once more, lone pair on this end, right? The end is directly bonded to a pi system here. So the lone pair will also be found in the p orbital, and they are parallel now, they are adjacent, they will sideways overlap, which means this lone pair suck into the benzene ring and not available, okay? So phenylamine compared to primary amines, phenylamines are definitely less nucleophilic, but primary amines are more nucleophilic, okay? And then I have this here. Mr. William, could you just quickly bring me through this?
Yep, right. So it largely depends on the nature of the amine group. If you have more donating friends, then generally you tend to be a stronger nucleophile. But there's a catch, right? You can see that if I'm tertiary, right, tertiary, it should be more nucleophilic. It should be. But sometimes it may not be the case, because if you have too many R groups around the lone pair, what will happen is you will provide steric hindrance, and you will actually block the availability of the lone pair, right? So sometimes tertiary amines are not as nucleophilic as what we expect them to be. So at the end of the day, right, it really depends on the data that is given, right? So tertiary could be more nucleophilic, could be less nucleophilic. You really have to argue based on the data that's given in the question. Hey guys, now in the lessons we went through there are 4 different ways for us to form amines, alright, and we're just going to focus on 2 of them, 13.3 and 13.4, alright, come let's take a look. So if you go to 13.3, you will notice what we're trying to do here is we're trying to form amides from amines. Now what are amides functional group? You will have this, a C double bond O that's bonded to a carbon with a nitrogen. Right, so there are different ways for us to do so. You could be using like a primary amine, you can be using a secondary amine, and the only reagent that is okay for us to form this is by using acyl chloride. Right, so there are 2 ways where you can learn how to form the final product. We did learn the circling way and also the mechanism way. So let us just recall both ways with them. Right, so I'm going to do this. Now the circling way, which is the easy way, is really just circle away one H and one Cl. So the rest of the stuff, just join them together. You're going to form the amide as well as HCl as the byproduct of this reaction. But bear in mind, whatever circling that we have learned, what happens behind the scene is always a nucleophile attacking an electrophile. Right? So Mr. Tim, who is the nucleophile in this case?
Well, lone pair on N, nucleophilic.
Exactly, right? So we have this lone pair on the nitrogen. Can you walk us through where's the electrophile?
So I see again a C bonded to a very electronegative O, very electronegative Cl. That's definitely your electrophile.
Alright, so once we have the nucleophile, the electrophile, the attack is going to take place. Right, so we expect the nucleophile to be attacking the delta plus carbon, and then you're going to kick chlorine out as the living group, join the rest of the stuff together, and then you're going to form the amide. Right, so this is the only way where you can form amides. Right, so Mr. Tim, can you walk us through 13.4?
Hey, of course, come, let's go. Now in 13.4, okay, simply put, we have a phenylamine, right? We're going to react it with aqueous bromine to get 2,4,6 tribromo phenylamine, okay? Now, before we start this, I'm just going to very quickly recap on how benzenes, right, actually react with bromine. So tell yourself this, if I have a benzene here, we need to use this thing called a halogen carrier catalyst, right? Why? Because benzene, they're actually very, very weak nucleophiles because they're resonance stable. So for your benzene to actually react, the halogen carrier catalyst needs to pull away one of the BRs to generate your Br+, okay? So the benzene can attack. Now, if you look at this reaction, you have phenylamine, we don't need a halogen carrier catalyst, right, Mr. William?
Yes, right. The reason is you look at the friends that they have, and you notice we have a NH2, right? So what's the nature of NH2? NH2 is strongly electron donating. All right. So what it does is it's going to push lots of electrons into the benzene, and the benzene becomes powerful.
Yeah,
right.
Very strong, right? So because it's a lot, the benzene in the phenylamine, it's a lot stronger of a nucleophile compared to your plain old boring benzene. You no longer need a halogen carrier catalyst, not useful anymore. So we can just react with aqueous bromine. Now, as usual, we have seen this in phenol. It's the same idea. You get a tri-sub. So 3 of the bromines comes in at the same time. You get 1 product, but tribromo, 3 bromines coming in. Okay. Now, Remind me again, Mr. Willem, what color is this 2,4,6-tribromo-phenylamine?
It's going to be a white precipitate.
Yes, perfect. It's a white PPT. Okay? And like I said, this is the exact same thing, right, with phenols. Right? We've seen this in phenols. Okay? Oh, me. Oh, shit.